Hi, my name is dr. Ahmath. Today we are going to discuss about sequences. So we are going to discuss about their properties, what kind of sequences are going to converge or diverge. But before we do that, let's discuss some of the popular applications of sequences. Namely, we're going to discuss about the binomial theorem today. Well, what is the infinite sequence? A sequence can be thought as the list of numbers which are written in some order. There is a law in which we are going to derive every number in this list. And the infinite sequence is the sequence which never ends up. So usually the sequence is going to be given in the form of a1, a2, and so on, an, where the formula to derive the nth element of a sequence is going to be given like this, for example. So let's derive a couple of elements of this sequence, where n goes from 1 to the infinity. So when n is equal to the 1, what we get is, say, 1 divided to the 2. Well, when n is equal to the 2, it's going to be 2 divided to the 3. When n is equal to the 3, it's 3 divided to the 4, and so on. So we can write down the values of the sequence like this. Well, there are a lot of applications of the sequences, and one of them is expansion of functions to the polynomial. So we are going to discuss about this today and tomorrow. And one of the easy and popular applications of the expansion of the functions into the polynomials is so-called binomial theorem. Well, you probably know how to expand x plus 1 in the square. So in order to do that, you have to multiply x plus 1 to itself 2 times. If you multiply x plus 1 to itself, open the brackets and simplify the terms, you're going to obtain x squared plus 2x plus 1. Well, probably can do the x plus 1 in the cube expansion as well. You have to multiply x plus 1 to itself 3 times, which is going to be x plus 1 times the x plus 1 in the square, right? You have to multiply x plus 1 to this term. And if you multiply all the terms and simplify them, you're going to get the following polynomial, where polynomial is the combination or linear combination of power functions. So let us fix this. A polynomial is a linear combination of power functions. So power function is any function which is written in the power x in the power of n as in power function. And the polynomial is the combination of many this kind of power functions. A0 times x in the power of 0. X in the power of 0 is 1. You can see here that x plus 1, it appears, is the polynomial of second order, which basically means that the highest term is going to be x squared, and then there is a term with the x, and at the end it ends up with the 1. Similarly, if you just expand x plus 1 in the cube, you're going to get a polynomial of the third order. The highest term is going to be x cubed, then there is a term with the x squared, x, and 1. Well, can you guess if you are going to expand, for example, x plus 1 in the fourth power, well, that's going to be the polynomial of the fourth degree. It means that the highest power is going to be x in the power of 4. Then there is a term with the x cubed, x squared, x, and 1. Similarly, if you expand x plus 1 in the power of 5, you're going to get again the polynomial, linear combination of the power functions. Well, you can see here that it is not, so there is a pattern for all of this polynomial, and the pattern is that there is always the term with the x in the power of n, x in the power of n minus 1 until the 1, and the only difference, for example, to this polynomial and this polynomial are the coefficients before x in the power of n. For example, the coefficient before the x in the power of 4 here is just 1. Well, here in the next polynomial, the coefficient before x in the power of 4 is 5. So one of the ways how we can store this kind of data in a computer, for example, to just store the coefficients. For example, you can store x plus 1 in the power of 4 as just the vector 1, 4, 6, 4, and 1. or you can just store x plus 1 in the cube just as a vector 1, 3, 3, and 1. Or x plus 1 in the square can be stored as the vector 1, 2, 1, right? So all of them are the coefficients of the power functions when you're going to combine them into a polynomial. So people have figured out that they don't need to store all of this x in the powers in order to represent the polynomials, in order to expand the powers of the x plus 1. What they can do is they can just store these coefficients only. And if you just look to all of these coefficients, they are going to be similar to these numbers. And if you just put all of these numbers, coefficients of the power functions all together, you're going to obtain so-called Pascal's triangle. So people knew about Pascal's triangle for ages, and they've been using this Pascal triangle in order to represent the powers of the x plus 1 particularly. So how to derive the Pascal triangle? So well, in order to derive this, you have to just add two adjacent numbers from the top row in order to derive the number in between. For example, here, you have to add these two ones in order to derive this number here in between, which is going to be 2. And then in the borders, I'm just going to copy 1. So here, 1 plus 1 is going to be 2. And the borders, I'm going to write 1 and 1. Well, in order to derive the next row, I'm going to do the similar operations. I'm going to just add these two numbers. It is going to be 1 plus 2, which is 3, 1 plus 2, which is 3, and then on the borders, I'm just going to write 1 and 1. Well, if you remember, x plus 1 in the cube is going to be expanded as x cubed plus 3x squared plus 3x plus 1, 1, 3, 3, 1. Or x plus 1 is going to be expanded as x squared plus 2x plus 1 is 1, 2, 1. Right? Similarly, you're going to obtain the other rows of the Pascal's triangle. So 1 plus 2 is going to be 3. In order to derive the next row, I'm just going to add 1 plus 3, which is going to be 4 in this case. 4, 6, 4, 1. 1, 5, 10, 10, 5, 1. Well, you can see here that you can derive rows in this way. There is a similar pattern which you can derive. And you can use this in order to expand the powers of the x plus 1. Well, the problem is it requires you to store the previous row in order to derive the next one. Well, people have figured out how to derive the next rows of the Pascal triangle using so-called binomial theorem. Well, binomial theorem enables you to power up the sum of the two numbers. Well, in this case, if you would like to know what is the 1 plus x in any power k, we can use the binomial theorem. In order to derive this, it is going to be in this way. So 1 plus, so the next term is going to be kx. The next term is going to be k times the k minus 1 divided to the 2 times the x in the square. The next term is going to be k times the k minus 1 times the k minus 2 divided to the 3 factorials times the x cubed. I would like to remind you that the n factorial is just the multiplication of all of the integers starting from 1 until the end. For example, the 3 factorials is going to be 1 times the 2 times the 3, which is 6. Or 4 factorials is going to be a multiplication of all of the numbers, 1 plus 2 times the 3 times the 3 times the 4, or simply 24, and so on. Well, you can derive the terms of the binomial theorem like this. So the next term is going to be k times the k minus 1 times the k minus 2 times the k minus 3 times the x in the power 4 divided to the 4 factorials. The next one is going to be similarly k times the k minus 1, k minus 2, k minus 3, k minus 4 divided to the 5 factorials times the x in the power 5. Well, the thing is, the binomial theorem is limited. It is going to end up at some point. For example, if the value of the k is equal to the 3, in this term here, x minus 3 is going to be equal to the 0, and the whole term is going to be simply vanished. If k is equal to the 4, then this term is going to be 0, and the whole term is going to be 0. It's going to be vanished. So it's going to stop until here. Well, people knew about the binomial theorem for ages as well. The binomial theorem is, this theorem is called binomial because there are two nomials, and you're going to power up the addition of the two nomials. The binomial theorem enables us to power up the sum of any two values, in particular 1 plus x. Okay, so if you would like to derive the next row of the Pascal's triangle using the binomial theorem, you have to just substitute k to be equal to the 6. If the k is equal to the 6 here, it's going to be 1 plus 6x. The next term is going to be 6 times 6 minus 1 divided to the 2 factorials. The next term is going to be 6 times the 6 minus 1, 6 minus 2 divided to the 3 factorials, and so on. And it ends up, so can you guess when we are going to finish the sequence with the 6's? Well, it is going to be 6 times, it's going to be 6 times the 6 minus 1, 6 minus 2, 6 minus 3, 6 minus 4, 6 minus 5 is going to be divided to the 6 factorials, is going to be the last term, because the next term is going to be 6 minus 6, which is 0, and all of the next terms are always going to have 6 minus 6 terms. So that is why there is no way to continue this. The number of the terms in the binomial theorem when k is an integer is limited. So if you just simplify this, you can derive the next row for the Pascal's triangle, which is going to be 1, 6, 15, 20, 15, 6, and 1. If you are going to continue using the binomial formula or binomial theorem, you can derive the next term and so on, the 7th row or the 8th row. Well, people knew about the binomial theorem for many, many years, and they always thought that this formula is true only for the k positive. When k is positive, the number of the terms in the binomial theorem is limited. But is it only necessary to use the positive integers? Well, until 16th age, people always use this theorem with the positive integers, with the k positive as a positive integer. And in 16th age, in 16th centuries, Newton has figured out that they can use this formula using the negative values of the k. Well, if you just substitute the negative value for the k, for example, k to be equal to the minus 1, then this sequence or this term is becoming an infinite term. Well, let's see how it's becoming an infinite term. If you remember the binomial, so the x plus 1 in the power of minus 1 is going to be simply 1 divided to the 1 plus x. And the terms were like this: 1 plus x, kx, right? The next term is k times the k minus 1. So let's just calculate this here. So the k times the k minus 1, when k minus 1 is going to be minus 1 times the minus 2, which is going to be simply 2 here. The next term is going to be minus 1 times the minus 2 times the minus 3 divided to the 3 factorials, right? Divided to the 2 factorials is going to be 1. And this is divided to the 3 factorials is going to be equal to minus 1, right? And the next term is going to be minus 1 times the minus 2 times the minus 3 times the minus 4 divided to the 4 factorials. It's going to be equal to the plus 1 and so on. And you can see here that the binomial theorem, binomial term, the x plus 1 in the power of minus 1, is going to have infinitely many terms. The terms are never going to be vanished. Previously, when k was a positive value, one of these terms, one of these brackets would be equal to the value of the k, and that just vanishes the term and all of the other terms just after that. Now, when k is a negative value, like minus 1, it will never end up. You can continue this until infinity. Well, if you would like to still approximate 1 divided to the 1 plus x using the polynomials, then you need to choose just some terms of this polynomial and cut it over the others. So in this case, 1 divided to the 1 plus x, it appears is going to be written as 1 minus x plus x in the square. It should be minus x cubed plus x in the power of 4, and so on. So there is obviously a typo here. It's going to be minus here, then plus, minus, plus, minus, plus, minus, and so on. Well, Newton has figured out that it is possible to use the negative integers instead of k. Then later on, he has figured out that it is true to use just the real number instead of k. It is not necessary to use integers. They could use the rational numbers instead of k. So he has figured out that it is possible to use k as a rational number, for example, 1 over 2. So if you just substitute k was the 1 over 2, what you're going to get is simply the square root of 1 plus x. So it enables us to approximate the values of square roots of any value, for example, square root of 2. You probably know how to find the square root of 2, right? You can just get any calculator and find the square root of 2. But have you been curious to know how your calculator figures out what is the square root of 2? Well, it appears it uses the sequences, infinite sequences. So it uses the binomial theorem where k is going to be just 1 over 2. So let's derive a couple of terms of this sequence when k is equal to 1 over 2. So if k is equal to 1 over 2, this term here, if k is equal to 1 over 2, this term here is going to be 1 over 2x. The next term is going to be 1 times to the minus 1 over 2 divided to the 2 factorials, which is going to be 1 over 4 in the power of x in the square with the minus, or 1 over 8, right? So the next term is going to be 1 times to the minus 1 over 2 minus 3 over 2 divided to the 3 factorials. Oh, well, it's going to be 6, right? So it's going to be 1 over 16 times the x cubed. So I'll just stop here because you can continue this until infinity. And if you would like to get more precise formula or value for your rational number, square root of 2, you can get more and more terms of your polynomial. Well, here, if you just use only these 5 terms, you just use a calculator in order to derive square root of 2. Well, first of all, in order to find the square root of 2, you have to figure out which value of the x you need to use. Well, here we have to use x to be equal to 1 so that 1 plus 1 becomes square root of 2. Since you have to substitute 1 instead of x in the left-hand side of your equation, you have to do the same with all of the terms, all of the appearances of the x on the right-hand side part. So this is going to be 1 here, 1, 1, 1, and 1. Then I'm just going to use the approximation of the square root using the binomial formula, which never ends up. I'm just going to cut only, I'm going to just use only 6 terms. So 1 over 16 minus 5 over 128. Then I'm just going to use a calculator in order to find the decimals of all of these numbers. And if I simplify this, it is going to be equal to the 1.4245. Of course, it is very rough approximation of the square root of 2, because if you just use a calculator, it's going to be a little bit different number. So it's just started 1.4142 and so on. But believe me, if you just use more terms of this polynomial, you're going to get more precise value of the square root of 2. So that is one of the really popular applications of the sequences. And today and tomorrow we are going to discuss about the sequences. Another application of the sequence is when you are going to expand the functions into so-called Taylor series, where again it's going to be a polynomial where you're going to just predict the values, the coefficients of the polynomials. Well, I hope that this lecture was interesting for you, and now you're even more interested in the sequences. Thank you very much.